Good afternoon, everybody, and welcome to our webinar on reducing leakage using data to inform on current incidents and predict future ones. My name's Ruth Clark, and I'm a business development manager within the Advanced Infrastructure Analytics team within Xylem. And I'm providing an introduction to this webinar, and then I'm going to hand over to my colleague Mike Allen, who will then talk us through the detail of how we can use data to detect leaks and bursts within a water distribution system. So firstly, if I just give a brief word on who Xylem are. Xylem was spun off from ITT in 2011, a company that's been involved in the water industry for well over a century. Most of you may know Xylem best for flight pumps and for many of our treatment products such as flight mixers or sanitaire blowers. Over the last 5 years, however, Xylem has become much more involved in decision intelligence technologies and has acquired a number of companies to provide a portfolio of solutions aimed at improving the operation of assets and the operations of assets which are owned and managed by water and wastewater utilities. One of these companies that Xylem acquired was Vicenti, a company that Mike Allen, who will soon be speaking, was one of the founders of. Utilities around the globe are collecting enormous amounts of data, but not necessarily making as much use of it as they could. Our decision intelligence solutions are aimed at making use of this data in order to enable utilities to operate their systems more efficiently, and where possible, to draw insights and predictions from that data. These tools allow utilities to move much more easily from reactive mode to predictive mode. So why is there a need for these decision intelligence solutions? Currently, particularly within the water industry in the UK, there is a drive to do more with less. So to reduce leakage, to reduce pollution incidents, but also to reduce costs. And detecting bursts quickly and identifying growing leaks before they become bursts can help utilities reduce leakage from their systems with minimal impact on the customer. Detecting customer-side leakage as well as the under-registration of consumption meters can also help utilities understand their systems better. This webinar explains Xylem's approach to helping utilities monitor their distribution networks and to help reduce non-revenue water. I'm quite sure that many of you will have questions during the webinar, and rather than interrupt Mike whilst he's presenting, we will have time at the end of the session for questions. Please do feel free to ask any questions via the chat box during the webinar as they come to mind, and I'll make a note of them and ask Mike at the end. If time is limited, and we don't have time to answer all those questions, I will collate those and disseminate the responses afterwards. I'll now hand over to Mike, who's going to talk us through the process.
Thanks, Ruth. So to pick up on Xylem's decision intelligence strategies again, there are 6 main strands to this. Reducing system losses, which is focused on reducing the system losses in a comprehensive and cost-effective way. Proactively managing your assets. Ensuring quality from source to tap. Managing the urban watershed, focusing on reducing the total cost of compliance with clean water regulations. Advanced water equity, so sustainably aligning system operations with stakeholder policy objectives, and gain control of your data, which is really unlocking the power of the data that you have and the data you're going to have in the future to have more effective decisions. So what I want to focus on today within decision intelligence is 3 of those petals. Gain control of your data, reduce system losses, and proactively manage your assets. And I want to talk about those in the context of smart water analytics. So where we're heading with this is understanding where problems are in the network and then getting to them faster. So meaning being more proactive. Predicting better where problems are going to be, so being more predictive. And then leveraging legacy data sources and existing investments in instrumentation, making the most of now and future investments. So I want to give a few examples of where this has been valuable across the world. The first one I'd like to pick up on is the South Australia water in Adelaide. They embarked on an initiative a year ago or a couple of years ago, to heavily instrument their central business district with a lot of smart water network instrumentation. So that means acoustic sensors to listen for leaks, flow meters to understand all the volume going into the area, smart meters, water quality sensors, and also pressure, transient, and hydrophone sensors. What they were trying to do was understand, can they get to leaks and bursts quicker? Can they reduce the amount of reactive work they're doing? And can they make savings? So what they needed to do was pull all of this data together in this area, the central business district, using a smart water analytics platform. And in doing that, they were able to extract the maximum value out of the data from all this instrumentation. They, in the first year, were able to preempt 20 or more water main incidents. They reduced their reactive work by a significant amount and got a significant amount of savings compared to if they'd have been reactively repairing. So that was an example of making the best use of data in Australia. An example here is from Park City, Utah in the US. And this is about understanding where problems are with your smart water network data. So Park City, Utah had a demand of about 16.5 MLB, and they had a big hidden leakage issue. They knew there was leakage, but it wasn't surfacing, and there were some hard to locate areas within the geography where they suspected the water might be going. So what they did was a 6-month campaign using pressure and acoustic sensors and combining that with real-time leak and burst detection analytics to turn the lights on in that area, to understand where are the leaks and bursts happening. During that 6-month period, they were able to find 1.1 MLD of leakage that hadn't surfaced at a cost of about 57K. And they reckon they've saved about 160K in operating costs per year in doing that. Finally, I'd like to give an example of predicting where problems are going to be. So there's a private water utility in Singapore that operates a relatively small network of mainly steel trunk mains to several industrial customers. And they found they were having lots of pipe bursts that were not easy to explain and on very new pipe. What they wanted to do was understand what's going on in the network. They deployed a set of high sample rate pressure sensors to look for pressure surges, and then deployed a set of advanced analytics. And they were quickly able to see that there were operations and activities going on in the network that were causing severe stress on the pipe, large magnitude and frequent transients. Now that they could see that, they could track it back to the sources of these transients and take mitigating action and reduce the impact of these transients and any future ones. And that was a variety of solutions, including pressure transient dampeners, as well as changing pumping and valve opening cycles. And they think that they have saved several $1 million compared to the cost of having to reactively replace pipe again, by understanding where the problems are and where future problems will be. So all of these things tying up again to smart water analytics, it's really about detecting and locating pipe bursts faster, so being more proactive, about tracking and prioritizing pipe leaks before they become bursts, so going back to that reactive versus proactive, improving asset lifetime by supporting a better asset replacement strategy and avoiding unnecessary pipe replacement. And then finally, maximizing the benefit of existing instrumentation, but also understanding future instrumentation investment as well, maximizing the use of the data that's available. So I gave a couple of case studies at the start, but there are utilities all over the world employing smart water networks to be more proactive and more predictive. A few examples are shown here. So Australia, as we mentioned before, from 2017, bringing all their data together in a smart water analytics platform. You've got Singapore. Since 2011, they've had a smart water network across their country to to provide decision support and also real-time leak and burst detection. And in Sharjah, a smart water network deployed to help monitor and address their non-revenue water. And then in Malaysia, a network of a couple of thousand pressure and acoustic sensors for real-time leak and burst detection. So all of these utilities are deploying extra instrumentation, trying to get the best use out of their data because they need actionable information. They need to get from that data to something that can help them make a decision about how best to efficiently operate the network. And so that comes down to having the right data at the right frequency, taken at the right time, in the right place. So in this case, about having the right instrumentation within the network, transmitting it to the right place, a centralized area where the data can be analyzed in terms of dashboard reporting, understanding levels, but also analyzing that data and trying to pull out meaningful events that are happening in real time or over a longer period. But then also understanding how are these things potentially going to be problems in the future. And all of this is focused on having actionable information that can be used to make important decisions about how to most efficiently operate the network. Proactive and predictive operation is incredibly important when considering leakage, because there are a lot of things that can be done to reduce leakage in the network, especially in the UK here. Things like sectorizing the network, making sure that those sectorized networks areas are correctly instrumented, having targeted leak surveys, assessing the condition of high-value pipes, understanding commercial losses of continually log customers, pressure management, and so on. And all of these things are reducing the leakage within the network, and they're all activities to get the non-revenue water down. But when the non-revenue water is down to an acceptable level, then the challenge becomes about maintaining it. And that is when it is very key to have instrumentation, delivering real-time data, and having analytics and systems that can process that data in a timely way to be able to make actionable information decisions. So in terms of gaining control of your data, and specifically on leakage, it's about leveraging the real-time data that may already be there within the network, so SCADA data, DMA level data, but then also the newer types of loggers that are supporting smart water networks, so transient sensors that are detecting very sharp changes in pressure, traditional pressure level type sensors, and also acoustic loggers or hydrophone sensors, both within the trunk main and transmission mains, but also within the distribution network. And also leveraging those other data sources such as smart meters that can be used not just to understand the customer's consumption, but flag up potential customer side leakage issues. So the focus there is on having these data streams, understanding, pulling real-time alarms and events from this data, but then combining that data together. So it's not just streams of data and then streams of alarms, but data meaningfully combined together to understand root cause issues of potential leaks and bursts in the network. So the example that we show here in the distribution network is where traditionally you may be deploying acoustic loggers, pressure sensors, and the DMA flow meter being on the inlet, and then the customers either being continuously monitored or through smart meters. So there are lots of different types of instrumentation for measuring transients and acoustics, and here's an example of one that of Xylem's solution to this, where it's instrumentation for leak and burst detection combined in one that can be retrofitted to existing infrastructure within the network. And It's about sampling pressure at relatively high rates, so hundreds of samples per second, to detect potential burst events, and then also acoustics to listen to the noise in the pipe and understand, is there an elevated level of noise, and is it increasing and indicative of a leak? And when you have a network of these deployed, you also need GPS to be able to synchronize these devices to be able to combine their data and understand where potential events are occurring within the network based on understanding of the network layout. So the example shown here is one from the UK, deployed in a UK fire hydrant, connecting a pressure sensor. So I mentioned that we're measuring, in this example with these loggers, pressure transients and hydrophones. And the reason that you would want to be measuring acoustics and pressure is twofold. With pressure transients, very quick changes in pressure, you're interested in instantaneous potential failures of pipes, so bursts, and responding to them as quickly as possible. Whereas with hydrophones and acoustic loggers, you're interested in understanding, is the noise level increasing over a longer period of time in a way that may be indicative of leaks? And so each of these parameters have different levels of suitability for those kind of problems. So with pressure transients, the detection and analysis can be done 24/7 because it's not affected by ambient noise, although lots of pressure transients are due to normal activity in the network. But with pressure transients, you can localize events based on several sensors detecting pressure transients occurring in the network, and they really are about understanding and responding to things quickly. Whereas with hydrophones, they are deployed at a closer distance than you would with pressure sensors. So about 1 kilometer for pressure sensors, and maybe up to 500 meters with hydrophones, depending on the pipe material. But hydrophones, when listening to noise, are more effective when listening at night, when it's quieter. So why do real-time burst detection? And so the idea is to reduce the runtime of catastrophic events, minimize the potential for damage, and also maintain the image. And so it helps understanding and proactively responding to events as soon as they happen, rather than learning about it when the event surfaces. So any time that can be saved detecting and responding to an event before it has surfaced is incredibly valuable. So how is that done? Well, it's the real-time measurement of pressure within the network from several sensors deployed in the distribution network, and then knowledge of the structure of the network, so how the pipe network is all interconnected, the materials of the pipeline, and then when an event is detected on the network. And so this is where the analytics come in. The analytics are understanding what the normal behavior of a pressure signature is at a given location, what's normal across every day, every hour. And then when something is abnormal, this raises an event. And several events detected across a network in a very short time space can be correlated and then referenced to the network to understand where did potentially this event come from, and does it look like a burst? Does it give confidence that this is a pipe burst? So you can see an example of it here with a pressure transient drop and several other sensors also seeing the same drop. And this is occurring over only a very couple of seconds worth of time. And then the event being localized to a specific location. I want to turn to leakage for a moment. So when we talk about leakage, it's about understanding the acoustic noise trends. So learning what is normal acoustic levels within the network at these particular sites, understanding what the changes are like, and then understanding when there is an abnormal or growing change. And obviously, the localization accuracy for leak and burst for leak detection is really dependent on how close you have the sensors and the type of material of the pipes. But the goal here is to understand the trends that are going up and issue alarms along the way, so that the utility can understand and track the growth of a leak. And so this is really aimed around being able to fix a leak before it develops into a pipe burst, which will obviously require a lot more reactive resource cost. So here's an example of how that works. So let's say that you're collecting data every hour or every day. What you are doing, you can track the increase in noise over time. And as this gets larger and larger, you become more and more confident that this is a leak rather than just a change in ambient noise caused by cars or other kind of ambient noise. And you can see here an example where the noise has increased, and then the leak has been identified and then repaired, and then the validation can be repaired with the validation can be seen of the repair by the drop in the acoustic noise. So another example here from this of the value of having fixed networks for leak detection. In this case, you can see across the top in the grey a pressure trace, and then in the green the acoustic noise signature. This is taken over multiple hours over several days, and you can see the noise level increasing, giving a high indication that there is a leak nearby. And then the leak was found, and the drop in pressure was due to the pipe isolation to repair the leak. And then after that, there's a validation that sure, the leak has been detected, but then another leak appears to develop nearby because the hydraulic condition of the network has changed, and it becomes quite common to see other leaks appear around this time as well. And so again, you see this, and an alarm is raised as the trend rises up, and then again the leak is found, and then no noise validated after the repair. But it's not just about detecting leaks that are growing over time. It may be that when sensors are installed and their lights are turned on in a DMA or within the distribution network, there's already high acoustic energy, and it may be from some leakage that is there in the background and maybe running off and not surfacing. And an example here is exactly that, where sensors were installed and the noise level was very high, tracked over multiple days. And leakage, this indicated the area where the leakage should be looked for, and a location was found within a DMA, but a hidden leak that had not surfaced and was actually the cause of a lot of water loss within the network. And this utility would save about 50 million litres a year from having detected this hard to find leak that, because it wasn't surfacing, they never would have found. But it's not just about detecting in-network leaks, but also understanding are there leaks on the customer side? And this can be facilitated by leveraging smart meter data sources, which are becoming more and more common in the UK now and across the world, and are incredibly valuable for a variety of reasons. If we think about it from a individual meter level, it's about understanding are there any abnormal trends occurring on an individual meter, being able to aggregate potential leaks together to understand an aggregate leakage estimation for customer side. What you can see on the right hand side is a couple of examples of interfaces for managing customer leaks. So the top one is looking at analytics for detecting customer leaks based on a normal consumption profile, and then identifying a significant deviation away from that consumption profile, and then enabling the management of that that identified leak within the system. So not just detecting that there is an issue and flagging it up, but providing a lifecycle management of dealing with this leakage event. The example taken from the bottom is to identify high nighttime consumption, which can be a very good indicator of a background leakage that maybe is not known by the utility or by the customer, but can be unveiled when looking at smart meter data. And so there, you're able to understand during the time when it should normally be quiet based on the type of the customer, are we seeing a sustained level of consumption that may be indicative of leakage, and then that can enable the utility to explore further with the customer, engage further with the customer to help them. Bringing several smart meter data sources together with traditional DMA monitoring, so it's flow meter going into DMAs and continuous logging of larger CNI customers, really allows a much higher resolution, better understanding of leakage within a network. So understanding management at a DMA level, understanding the dynamic water balance, and taking advantage of that higher resolution, higher frequency data, and also being able to break down the level of leakage in terms of network side leakage and customer side leakage. So the example here of a dashboard that's tracking this over time across several DMAs, and understanding what level of consumption has come from smart metering, what level is being estimated due to not having a smart meter or knowing the readings, and then the level of estimated customer side leakage and network leakage. And then also with this real-time data combined together, you can show trends on individual DMAs, and then also understand a traditional water balance that can be dynamically updated. So it's really about pulling all of those data sources together to be able to facilitate this and building up the analytics from a meter level all the way up to a DMA level. So a key thing here in leveraging these different data sources that are available or become available to a utility is how you would combine them together to make the best use of them to reduce false positives and understand whether something is a real event or not. So in this example, if we look at the top graph, the system is learning what is normal for a inflow into a DMA, understanding what the usual consumption is, and then flagging up in an intelligent way, so not based on a fixed threshold, but understanding a deviation from the normal condition, flagging that up in the green line here and saying, okay, this looks abnormal. What can I do to verify whether this is a leak or not? And so you can look, the system can then look to the aggregated consumption that it knows about from the network and say, does it look like this is a change in consumption? If it isn't, then that gives an indication that this may be leakage. So what you're seeing here expanded a bit is on the bar chart is the difference between the consumption and the inflow. And so this gives an indication that yes, it is actually a leak or a burst event. But now if there are smart other instrumentation within the network, such as hydrophones that are collecting data maybe multiple times per day, that increase in flow can be correlated with the acoustic noise as well. So that gives another layer of indication as to whether there may be, this is really a leak or a burst. And then the final validation that can happen here is the correlation with pressure transient data, like we spoke about before. And so when you are seeing an abnormal change in consumption correlated with an acoustic event and a pressure transient event, it gives a very high indication that this is indeed a burst and can be responded to quickly. So a lot of what I've spoken about up to this point has been about how can existing data and smart network data be pulled together in a real-time context. So understanding from a control room or quick leak response kind of scenario, are there events in the network, where are they occurring, and then getting there quickly. So the actionable information in these cases is about being proactive and understanding where the events are quickly and with a high confidence. But that same data that's being used to understand things in real time can be useful over a longer time period to understand where there may be issues in the network in the future. So if we take the pressure transients, for example, pressure transients are a contributing factor to the eventual failure of pipes, among other factors. But if a pipe is seeing very sharp pressure changes of large magnitude very frequently, then that is a good indicator that there is excess stress on the network around where the sensor is, and so the network is not calm. So if you can analyze these transients over time at individual sensors within a DMA, and you can look at all of that stress, you can relate it back to the pipe network. So what material are the pipes made of in the surrounding area? When were they installed? What is the leak history like and the burst history around that area? And yes, how old are the pipes? And you can relate that then to a risk factor, identifying certain areas in the network that may be at higher risk of failure because of the stresses that they're seeing. Now, if you remember, we were using pressure transients to localize burst events previously, but that same procedure can be used to identify sources of pressure transients, which may be industrial customers or heavy use commercial customers. So once the utility knows about that, they're able then to make an intervention, to be able to mitigate the problem by working with the customer to understand how they can reduce the impact of transients. And so this also can be correlated with consumption data when it's available, so smart meter data or CNI data. Now, just a couple of examples of the kind of transients that can be seen. Pressure transient sensors become really helpful because traditional ways of monitoring pressure are maybe to take a measurement every minute or every 5 minutes or every 15 minutes. Now, if you think about the speed that a pressure transient caused by, let's say, a pump coming on or a valve opening quickly, this can occur over only a very few seconds. And so if you're taking measurements every 15 minutes or every 5 minutes, you're effectively going to smooth out the impact of that transient, and you won't see these large deviations that are a cause for concern within pipes and may contribute to their eventual failure. And you can see it's not just about understanding the magnitude, but also the frequency of these transients as well. So that's why it's important to be able to track it over time, and why pressure transient sensors, for example, are very useful in this case. A few more examples of very large pressure transients that, when they're seen, are an immediate cause for concern within a network and give rise to having to resolve an issue very, very quickly. When you have this knowledge of areas that are at risk in the network, and you know that pressure surges can be correlated with bursts and leaks within the network because they're having an impact, you can start to be more proactive in terms of being able to target better leakage surveys based on high areas of stress where there may be leaks developing. And also understanding where in the network is not under so much stress, and actually can we deprioritize the repair and replacement of assets that don't appear to be under a lot of stress, and prioritize the ones that definitely are under a lot of stress. So a few examples here are an overlay of identifying area of risk, and then the validation that leaks and bursts within the area, which are these little stars shown here, were related to customer activity within the network. And you can see that the impact of these pressure transients can travel over quite a large distance, but it can be very helpful to understand where the areas of the risk are, and also areas that aren't seeing as much stress. So just to summarize with the proactive side, it's helpful for predictive assessment using pressure transients, consumption data, and the GIS information within the network to be able to understand areas in the network where there may be high risk and target leakage activities or repair and replacement, but also being able to mitigate and root cause those problems by being able to localize and identify potential customers or operations that are causing issues. So finally, I'd like to move a little bit away from the analytics side and talk about how there is a need here to have platforms that facilitate these kind of analytics and these kind of solutions. It's very common to see that a lot of different data sources within a utility, because utilities have made a lot of investments in existing enterprise data systems and also specific types of sensors to be deployed in networks for very specific goals. And there is a real value on being able to pull all of that data together to remove the silos between the different original uses of that data. And this is where the idea of a smart water analytics platform is really key. It's about being able to pull that data together, be able to understand how the data are correlated, be able to bring in legacy and enterprise data systems such as the GIS, potentially a hydraulic model, and other elements, and use that to make to give increased confidence in decisions based on the actionable information that are coming out of the smart water analytics that are being applied to these different data sources. And that can have value across a variety of different business functions, not siloing in terms of customer meters are just used to monitor demand and improve billing, but customer meters can be valuable to help root cause problem areas, identify customer side leakage, and help with the DMA level management. So a lot of the all the examples that I've gone through today, including our case studies at the start, have all been facilitated by Xylem's decision intelligence platforms, by our smart water analytics platform called View. And what View is doing is providing a smart water analytics platform that can do exactly the job that we discussed in the previous slide, which is integrating those disparate data streams and data from existing enterprise systems within an organization, pulling it all together in a way where the smart water analytics can combine and correlate the data in an intelligent way to make an informed decision, and delivered either in a cloud configuration or on-premise for a utility. And the interaction with all of these analytics is provided through a browser-based user interface and provides customizable dashboards and reporting, and also user and alert management, as we discussed with the smart meter event management and other leak and burst detection event management. The important thing there is being able to bring in a set of disparate data streams in a variety of different ways, occurring at a variety of different times, being able to pull all that data together, process it in a correlated way, and be able to manage and configure that system. But then also being able to make the output of those systems available to other existing systems, be it SCADA or other maybe dashboards are built through Power BI or other types of systems being built within a utility, or future systems that may be developed. So it's not just that the data ends up in the platform and all the information comes through a browser, but also that it can be plugged in to other systems within the organization. So an example of this is with South East Water. So South East Water in the UK were running a large deployment of smart water network technologies, and they needed to integrate data gathered by multiple sensors and meters, including meters running on FlexNet, NB-IoT, and 3G and 4G, and with their existing systems for billing, resource management, customer engagement. And so they specified a central management system that needed to be flexible enough to interface with all these different systems, and also powerful enough to handle all of the data that is generated by all this equipment, because you have an increased amount of data needs to be efficiently processed, and then provide actionable information from that, so alarms, analytics, and leak detection. And South East Water selected the Xylem View platform and is now operating in the South East Water data center. So what I'd like to do is just summarize where we've been over the last 40 minutes and discuss how we've been using data to inform current incidents and predict future ones. We spoke about how with smart water analytics you can be more proactive and more predictive, meaning that you can see events more quickly. You've turned the lights on in the area effectively, and you can see and respond to events more quickly, but that you can also use that same data to understand where there may be problems in the future. Now, Xylem helps you make the best use of the data that you have in being proactive and predictive, and helping you reduce silos within the organization through a smart water network platform. Now, View is Xylem's data-agnostic and delivered in the cloud or on-premise smart water platform, and that helps the utility support real-time decisions, longer-term planning. And the real key here is not just being able to make use of the data that you have today, but going on a journey with you and understanding how you scale up your smart water and investment in network instrumentation and functionality on a smart water network journey. So I'd like to leave it there at that point, and I can hand back to you, Ruth.
Thank you very much, Mike, for that very informative presentation. There's been a few questions that have come in, so I hope you don't mind if I put them to you.
Absolutely not.
Okay, so there's been a few that have come on in on a sort of common theme, so I'll sort of group those together.
Sure.
What density of sensors are required in a typical DMA, and other questions to do with the network coverage of pressure sensors, for example. I think you touched on it with one of your slides about hydrophones, etc. But perhaps you could just give a little bit more detail on that.
Yeah, of course. So the density that you would want to deploy pressure and acoustic sensors is going to depend partially on the complexity of the network, but predominantly on the materials of the pipes within that network. So if they're mainly metallic pipes, then that means that the pressure signals travel further, and so you can place the sensors further apart. And the same is true with acoustics, because in the metallic pipes, the signal will travel further than in plastic pipes, which tend to attenuate the signal. Now, between acoustic loggers, which are typically deployed outside the pipe without an interface to the water, and hydrophones, which have a direct interface to the water in the pipe, acoustic loggers would have to be deployed much more closely, and hydrophones can be deployed further apart because they are directly connecting to the water. So the water is carrying the sound that the loggers are listening to rather than the pipe itself. So with all of that said, nominally, you would space your pressure sensors around 1 kilometer apart from one another, and your hydrophone sensors typically around 500 meters. But then acoustic loggers of the magnetic type that you attach would typically be a couple of 100 meters apart.
Okay, thank you very much. I've got a couple more, if that's okay. One question is the source of pressure transients identified from the sensors only, or is it additional information required?
Good point. Yeah, so the transient information comes from the sensors. So what happens there is you have this real-time data trace, which is analyzed, and these very sharp changes in pressure are identified. But to give that data more context, you need to understand where is that data coming from, where are the transient sources themselves coming from, and that context comes from having multiple sensors that are detecting an event within the network. And then you can get further confidence that you know what the root causes of those transients in a predictive sense by correlating it with consumption records if they're available. So basically every extra data source that you add gives you more context to help understand what the root cause of the event may be.
Thank you. And I think we've got time for one more, which is how would you handle scaling up? A large UK water utility might need thousands or tens of thousands of sensors.
Yes, absolutely. So there are a few things to consider here. The first one I would say is that you probably wouldn't need the same density of instrumentation across the whole of the network. Obviously, where networks are in the UK vary very drastically in terms of the conditions where they are, but rural versus urban environments. You tend to need higher density of sensors in more complex urban environments and less sensors in more rural environments. But depending on how the instrumentation is intended to be used, it may be that you are only temporarily deploying certain sensors. But it's true that for a full scaled up network that involves thousands of sensors, you have to manage the instrumentation the same way that you would with the same way that acoustic logger management is managed today, with the investments that utilities have made. I would say when we're talking about transient sensing and monitoring within DMAs, you can think of the real-time detection as being this kind of understanding where something is very quickly and responding to it, but the kind of predictive element that takes advantage of that same data as almost being like a health check within a DMA. And so you can imagine a strategy where you can have sensors that you can move around to do health checks on DMAs and combined with a set of fixed sensors that may be left in the DMA as a kind of a sentinel.
Great, thank you. One very last short one. What is the forecast return on investment implementing the Xylem View platform?
So this really depends on how the platform is being used and what the costs are related to the specific activities that utilities are doing, right? So we gave an example earlier on with South Australia Water, where they were able to reduce their reactive events. So they obviously have costs associated with reactive repairs, and if they're able to reduce those, then there's a good return for them on because they're significantly reduce their overall cost, but it's really tied to how much it costs them to do it. And the same is true in terms of the predictive element. So understanding there how much money can be either saved or expense deferred for an asset replacement is really down to how much that costs that individual utility to do that work. I hope that answers the question, but happy to discuss further after the meeting.
Okay, I think we're going to draw it to a close now. I'll make sure that any remaining questions, because there are a few more, are answers and that responses are sent out to the attendees. If you have any further questions going forward, if one pops into your mind in 5 minutes after this webinar is finished, then please do feel free to contact me. My email address is there on the screen, and I can certainly sort out getting any of those questions responded to. So without further delay, I'd like to thank you, Mike, once again, and thank all of the attendees for taking time out of your busy schedules. I hope you found it useful and informative, and I look forward to hearing from many of you in the coming days. So I'd like to say goodbye now. Bye-bye.
Thanks, everyone.